In statistics, Spearman's rank correlation coefficient, or Spearman's rho, named after Charles Spearman and often denoted by the Greek letter ρ, is a nonparametric measure of statistical dependence between two variables. It assesses how well the relationship between two variables can be described using a monotonic function. If there are no repeated data values, a perfect Spearman correlation of +1 or -1 occurs when each of the variables is a perfect monotone function of the other. Spearman's coefficient, like any correlation calculation, is appropriate for both continuous and discrete variables, including ordinal variables. Spearman's and Kendall's can be formulated as special cases of a more general correlation coefficient. Definition and calculation. The Spearman correlation coefficient is defined as the Pearson correlation coefficient between the ranked variables. For a sample of size n, the n raw scores are converted to ranks, and ρ is computed from where is the difference between ranks. See the example below. Identical values are assigned a rank equal to the average of their positions in the ascending order of the values. In the table below, notice how the rank of values that are the same as the mean of what their ranks would otherwise be. In applications where duplicate values are known to be absent, a simpler procedure can be used to calculate ρ. This method should not be used in cases where the dataset is truncated, that is, when the Spearman correlation coefficient is desired for the top X records. The user should use the Pearson correlation coefficient formula given above. The standard error of the coefficient was determined by Pearson in 1907 and Gossett in 1920. It is related quantities. There are several other numerical measures that quantify the extent of statistical dependence between pairs of observations. The most common of these is the Pearson product moment correlation coefficient, which is a similar correlation method to Spearman's rank, that measures the linear relationships between the raw numbers rather than between their ranks. An alternative name for the Spearman rank correlation is the grade correlation. In this, the rank of an observation is replaced by the grade. In continuous distributions, the grade of an observation is, by convention, always 1/2 less than the rank, and hence the grade and rank correlations are the same in this case. More generally, the grade of an observation is proportional to an estimate of the fraction of a population less than a given value, with the half observation adjustment at observed values. Thus this corresponds to one possible treatment of tied ranks. While unusual, the term grade correlation is still in use. Interpretation. The sign of the Spearman correlation indicates the direction of association between X and Y. If Y tends to increase when X increases, the Spearman correlation coefficient is positive. If Y tends to decrease when X increases, the Spearman correlation coefficient is negative. A Spearman correlation of 0 indicates that there is no tendency for Y to either increase or decrease when X increases. The Spearman correlation increases in magnitude as X and Y become closer to being perfect monotone functions of each other. When X and Y are perfectly monotonically related, the Spearman correlation coefficient becomes 1. A perfect monotone increasing relationship implies that for any two pairs of data values xi, y and xj, yj, that xi minus xj and y minus yj always have the same sign. A perfect monotone decreasing relationship implies that these differences always have opposite signs. The Spearman correlation coefficient is often described as being nonparametric. This can have two meanings. First, the fact that a perfect Spearman correlation results when X and Y are related by any monotonic function can be contrasted with the Pearson correlation, which only gives a perfect value when X and Y are related by a linear function. The other sense in which the Spearman correlation is nonparametric in that its exact sampling distribution can be obtained without requiring knowledge of the joint probability distribution of X and Y. Example. In this example, the raw data in the table below is used to calculate the correlation between the IQ of a person with the number of hours spent in front of TV per week. Firstly, evaluate. To do so, use the following steps, reflected in the table below. Sort the data by the first column. Create a fourth column and similarly assign it the ranked values 1, 2, 3, n. Create a fifth column to hold the differences between the two ranked columns. Create one final column to hold the value of column squared. With found, add them to find. The value of n is 10. These values can now be substituted back into the equation, to give which evaluates to row equals minus 29 165 equals minus 0.175757575, with a p-value equals 0.627188. This low value shows that the correlation between IQ and hours spent watching TV is very low, although the negative value suggests that the longer the time spent watching television, the lower the IQ. In the case of ties in the original values, this formula should not be used. Instead, the Pearson correlation coefficient should be calculated on the ranks. Determining significance. One approach to test whether an observed value of ρ is significantly different from 0 is to calculate the probability that it would be greater than or equal to the observed R, given the null hypothesis, by using a permutation test. An advantage of this approach is that it automatically takes into account the number of tied data values there are in the sample, and the way they are treated in computing the rank correlation. Another approach parallels the use of the Fisher transformation in the case of the Pearson product moment correlation coefficient. That is, confidence intervals and hypothesis tests relating to the population value ρ can be carried out using the Fisher transformation. If F is the Fisher transformation of R, the sample Spearman rank correlation coefficient, and n is the sample size, then is a z-score for R which approximately follows a standard normal distribution under the null hypothesis of statistical independence. One can also test for significance using which is distributed approximately as student's t-distribution with n-2 degrees of freedom under the null hypothesis. A justification for this result relies on a permutation argument. PV-rank is a very recent R package that computes rank correlations and the p-values with various options for tied ranks. It is possible to compute exact Spearman coefficient test p-values for n26. A generalization of the Spearman coefficient is useful in the situation where there are 3 or more conditions. A number of subjects are all observed in each of them, and it is predicted that the observations will have a particular order. For example, a number of subjects might each be given 3 trials at the same task, and it is predicted that performance will improve from trial to trial. A test of the significance of the trend between conditions in this situation was developed by E.B. Page and is usually referred to as Page's trend test for ordered alternatives. Correspondence analysis based on Spearman's ρ. Classic correspondence analysis is a statistical method that gives a score to every value of 2 nominal variables. In this way, the Pearson correlation coefficient between them is maximized. There exists an equivalent of this method, called grade correspondence analysis, which maximizes Spearman's ρ or Kendall's tau.